In the autumn of 1997, a graduate student named Adam Rees was sitting at a computer terminal at Harvard University, running an analysis that he had been working on for weeks, trying to extract a clean result from a dataset that was almost pathologically difficult to work with. He was 27 years old. He had spent the better part of 2 years doing exactly this kind of work, measuring the brightness of distant exploding stars, calibrating out the various sources of systematic error that could corrupt the measurement, building up a sample that was large enough and clean enough to say something definitive about the expansion history of the universe. He was part of a team, the High-Z Supernova Search Team, led by Brian Schmidt, an American astronomer working in Australia, and they were in a race with another team, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, to be the first to measure the deceleration parameter of the universe from Type 1a supernovae. The deceleration parameter was a specific number, a number embedded in the equations of general relativity that described how rapidly the expansion of the universe was slowing under the influence of its own gravity. Both teams had been collecting data for years, both teams were close to a result, and Rees, running his analysis in the autumn of 1997, was about to become the first person in history to see what the data actually said. What it said did not make sense. The supernovae were in the wrong place. Not wrong in an obvious instrument malfunction kind of way. Wrong in a specific, directional, quantitative kind of way. They were dimmer than they should be. Distant Type 1a supernovae occurring in galaxies billions of light-years away, at redshifts high enough that the light had been traveling for a substantial fraction of the age of the universe before reaching Earth, were dimmer than any model of a decelerating universe predicted. And dimmer meant farther. The galaxies in which these supernovae occurred were farther away than they should be given how fast they appeared to be receding. The universe had been expanding faster in the past than in the present. It had not been decelerating, it had been accelerating. Something was pushing the universe apart, and it had been doing so for billions of years, and it was still doing it, and it was winning against gravity. Rees stared at his result. He ran the analysis again, he looked for errors, he checked his calibrations, his photometry, his redshift measurements, the way he was handling the light curves of the supernovae, the corrections he was applying for dust in the host galaxies, the statistical methodology. He could not find an error. The result held. He sent it to Brian Schmidt. Schmidt's first reaction was that there was something wrong with the analysis. This was not a dismissal of Rees, it was the correct scientific response. The result was extraordinary, and extraordinary results require extraordinary scrutiny. Schmidt went through the analysis himself. He could not find an error either. The High-Z team began a careful, systematic review of their data, checking everything that could be checked, looking for any systematic effect that might be masquerading as an acceleration signal. They found none. The data said the universe was accelerating. The data said it was accelerating. The data kept saying it. Meanwhile, across the country at Lawrence Berkeley, Saul Perlmutter's team was doing the same thing. They had more data, a larger sample of supernovae, and they had been at this longer, and they had built some of the key techniques that both teams were using. They ran their analysis. They got the same answer. The universe was accelerating. They also assumed initially that something was wrong. They also went through their data looking for errors. They also could not find any. By early 1998, both teams had convinced themselves, reluctantly and with extreme care, that the result was real. The universe was not decelerating, it was accelerating. The expansion of the cosmos was speeding up. Something was causing this acceleration, something that had the properties of a repulsive force operating throughout the universe, something that was winning against gravity on the largest scales, something that had not been predicted by any mainstream cosmological model, and had not been expected by any of the people who had spent decades building those models. The two teams published their results within weeks of each other in early 1998, and the announcement was one of the most significant in the history of modern astronomy. Science magazine named it the breakthrough of the year for 1998. Not because the accelerating universe was confirmed. 1 year of publications is not enough to confirm something this extraordinary, but because the evidence was good enough and the implications were dramatic enough that the scientific community recognized immediately that something fundamental had changed. The universe had revealed a property of itself that nobody had anticipated, and the property was going to require a rethinking of cosmology at the deepest level. There was something out there making up the majority of the universe's energy content, completely unknown, completely undetected by any means other than this indirect gravitational effect. They called it dark energy. And the name was chosen for the same reason that dark matter got its name, not because they knew what it was, but because they had absolutely no idea, and the name acknowledged the ignorance while giving it a label. To understand why the accelerating universe was so shocking, why even the people who discovered it assumed at first that they had made a mistake, you have to understand what was expected, and why it was expected, and how thoroughly the expectation was grounded in physics that had been confirmed many times over. General relativity, Einstein's theory of gravity, published in 1915, describes the relationship between the geometry of spacetime and the distribution of matter and energy within it. The equations, the Einstein field equations, determine how spacetime curves in response to matter and energy, and how the curvature of spacetime determines how matter moves. Applied to the universe as a whole, the Einstein field equations produce what are called the Friedmann equations, derived in the 1920s by the Russian mathematician Alexander Friedmann, which describe how the scale of the universe, the factor by which all distances are stretching, evolves over time. The Friedmann equations tell you that if the universe is filled with ordinary matter, or with radiation, then the expansion of the universe decelerates over time. Gravity, acting on all the matter in the universe, pulls everything toward everything else, and the net effect is to slow the expansion, not stop it necessarily, but slow it. The rate of deceleration depends on the density of matter. More matter means faster deceleration. A high-density universe would eventually stop expanding and collapse. A low-density universe would expand forever but slow down as it did. In between is the critical density, the density at which the universe expands forever, decelerating but never stopping. In all cases, with ordinary matter and radiation, the expansion decelerates. This was not a tentative prediction, it was a rigorous consequence of general relativity, a theory that had been tested in multiple contexts and had never been wrong. The Type 1a supernova measurements were supposed to measure the deceleration. They measured acceleration instead. The data was wrong, or the theory was wrong. The data turned out to be right. The theory, in the sense of the theory that included only ordinary matter and radiation and no dark energy, was wrong, or rather it was incomplete. Something was missing from the energy budget of the universe, something that the equations had not accounted for, something that produced not deceleration but acceleration. To produce acceleration in the Friedmann equations requires something with a specific and unusual property. Ordinary matter has positive energy density and positive pressure. Both contribute to the gravitational attraction that decelerates the expansion. Radiation, photons, neutrinos, has positive energy density and positive pressure too, in fact a larger pressure relative to its energy density than matter. Both matter and radiation decelerate the expansion. To accelerate the expansion, you need something with negative pressure, something with a tension rather than a push, something that pulls inward on itself while the space containing it expands. Something with sufficiently large negative pressure relative to its energy density produces a net effect in the Friedmann equations that acts repulsively. It pushes the expansion forward rather than decelerating it. The specific condition for acceleration is that the pressure must be more negative than -1/3 the energy density, in the units physicists use. Dark energy, as measured, has a pressure that is equal and opposite to its energy density, a ratio of pressure to energy density of exactly -1 or very close to it. This is the equation of state of a cosmological constant, the simplest possible form of dark energy, and the one that fits the current data best. The cosmological constant is where the story takes its most human and most poignant turn, because the cosmological constant was not invented in 1998. It was invented in 1917 by Einstein, and he called it his greatest mistake. When Einstein applied his field equations to the universe as a whole in 1917, he was working before Hubble's discovery of cosmic expansion, in an era when the universe was believed to be static, neither expanding nor contracting. A static universe was the expected state of affairs, the common assumption of the time. But Einstein's equations, as initially written, did not allow for a static universe. They predicted that a universe filled with matter would either expand or contract. It could not sit still because gravity would cause it to collapse. To prevent this collapse and allow a static solution, Einstein added a term to his equations, the cosmological constant, denoted by the Greek letter lambda, that represented a kind of background repulsion permeating all of space, a universal anti-gravity that exactly balanced the gravitational attraction of matter and allowed the universe to be static. Einstein was not happy with the cosmological constant. He found it inelegant. It was an extra term, with no physical motivation, added purely to make his equations produce the answer he expected from philosophical prejudice rather than from physics. But it worked, mathematically, and he published it, and it produced the static universe he wanted. And then, in 1929, Hubble showed that the universe was not static, it was expanding. Every galaxy was receding from every other galaxy, at a rate proportional to its distance, exactly as the expanding universe solutions of the Friedmann equations predicted. The static universe was wrong. The cosmological constant was unnecessary. Einstein removed it from his equations and reportedly called it his greatest mistake. Not because the cosmological constant was physically impossible, but because he had added it out of prejudice rather than necessity, and by doing so had missed the opportunity to predict the expansion of the universe, which his equations would have done naturally if he had trusted them. The cosmological constant sat in the dustbin of physics history for several decades, an embarrassing relic of a mistake, occasionally mentioned as an example of how even the greatest minds could be misled by philosophical assumptions. And then, in 1998, the supernova data came back, and what the data showed was that the universe was not just expanding, it was accelerating. And the simplest mathematical description of an accelerating universe was a cosmological constant, lambda. The term Einstein had added in 1917 for the wrong reasons and then removed as his greatest mistake. It was back, and this time, not as a kludge to produce a static universe, but as the measured property of empty space, a measured property that nothing in our current theory of the vacuum can explain. This is where the story deepens into one of the most embarrassing and most important problems in theoretical physics. The cosmological constant in quantum field theory is not arbitrary, it is a prediction. Every quantum field, every fundamental field in the Standard Model, contributes to the energy of the vacuum, the energy of empty space. This is not a speculative claim, it is a direct consequence of quantum mechanics. The uncertainty principle requires that quantum fields oscillate even in their ground state. There is irreducible zero-point energy, energy that cannot be removed, energy that is present even in the total absence of any particles. Every field has this zero-point energy. Sum up the contributions of all the fields in the Standard Model, every fermion, every boson, every field that quantum field theory describes, and you get a prediction for the energy density of the vacuum, which is mathematically equivalent to a cosmological constant. The prediction is not small. It is, depending on the cutoff scale at which you trust the calculation, somewhere around 10 to the 120 times larger than the observed value of the cosmological constant. Not 10 times larger, not 1,000 times larger. 10 to the 120 times larger. This is the largest discrepancy between a theoretical prediction and an experimental measurement in the entire history of physics. It is so large that physicists have given it its own name, the cosmological constant problem. And it is not a new problem. It has been recognized since the 1960s, when the connection between the vacuum energy of quantum field theory and the cosmological constant was first made explicit. It has been one of the central unsolved problems in theoretical physics for 60 years. The 1998 discovery did not create the problem, but it made it more urgent because it turned the cosmological constant from a theoretical curiosity into a measured physical quantity that any complete theory of the universe must explain. To understand just how extreme the discrepancy is, consider this analogy. Imagine you were trying to predict the height of the Empire State Building, and your calculation came out at the distance from the Earth to the nearest star. Not 100 times off, not 1,000,000 times off. 40 light-years off, in a prediction of a building that is 400 meters tall. That is the level of discrepancy between the predicted vacuum energy and the observed cosmological constant. The theory says the vacuum should be seething with energy, turbulent and dense with quantum fluctuations carrying an energy density that would curve spacetime so severely that the observable universe would be the size of a proton. Instead, the cosmological constant is tiny. Non-sewer, yes, but by a factor of 10 to the 120 smaller than the naive quantum field theory prediction. The vacuum is almost calm, almost flat. The cosmological constant is almost zero, but not quite. And the not quite is what is tearing the universe apart. Something cancels the enormous quantum contribution to the vacuum energy almost perfectly, leaving a tiny residual that is the cosmological constant we observe. What cancels it? What mechanism produces this extraordinary cancellation is completely unknown. Supersymmetry, if it exists, would cancel the contributions of bosons and fermions against each other, but the cancellation is exact only if supersymmetry is unbroken. And supersymmetry must be broken because we do not observe superpartners at low energies, and the breaking of supersymmetry reintroduces a cosmological constant that is smaller than the unsupersymmetric value, but still enormously larger than what is observed. String theory has been proposed to solve the problem, and it has a mechanism, the landscape of string vacua, an enormous number of possible vacuum states with different values of the cosmological constant, from which the observed value might be selected by anthropic reasoning. But this is contested and has been accused, by critics including Perlmutter himself, of being unfalsifiable. No mainstream theoretical framework has produced a compelling explanation for why the cosmological constant is the value it is. The problem remains completely open. The cosmological constant is the simplest model for dark energy, but it is not the only one. The cosmological constant is mathematically equivalent to a form of energy that has the same value at every point in space, at all times. It is truly a constant, a fixed property of the vacuum. But dark energy could also be something more dynamic, a field that changes over time, that has different values in different eras of the universe, that evolves as the universe expands. The generic name for such a field is quintessence, a fifth element, beyond the matter, radiation, dark matter, and cosmological constant of the Standard Model, a new form of energy with its own dynamics and its own potential energy function that drives the evolution of the dark energy density over time. Quintessence models make predictions that differ from the cosmological constant in a specific way. They predict that the equation of state of dark energy, the ratio of its pressure to its energy density, is not exactly -1 but varies over time, deviating from -1 as the quintessence field evolves. The cosmological constant has equation of state exactly -1 always, by definition. Quintessence has an equation of state that changes, that could be less negative or more negative than -1 depending on the specific model. Measuring the equation of state of dark energy, and determining whether it is exactly -1 or deviates from it, is therefore one of the most important observational goals in cosmology. It would distinguish between a cosmological constant and a dynamic dark energy field, and it would constrain the specific form of the dark energy potential if the field interpretation is correct. Current observations, from Type 1a supernovae, from the CMB, from baryon acoustic oscillations, from gravitational lensing surveys, are all consistent with an equation of state of exactly -1. Dark energy looks like a cosmological constant, with no evidence of evolution. But the precision of current measurements is not sufficient to rule out small deviations from -1, and the theoretical stakes are high enough that enormous observational programs have been designed specifically to improve the measurement. The Euclid satellite, launched in 2023, is mapping the large-scale structure of the universe with the primary goal of measuring the equation of state of dark energy to percent-level precision. The Dark Energy Spectroscopic Instrument DESI at the Kitt Peak National Observatory in Arizona has been measuring the redshifts of tens of millions of galaxies to map baryon acoustic oscillations and constrain dark energy with unprecedented statistical power. The Nancy Grace Roman Space Telescope, when it launches, will conduct wide-field surveys of weak gravitational lensing and Type 1a supernovae that will further tighten the constraints. In 2024, the DESI collaboration released its first major results, and the results were, in the carefully hedged language of science, intriguing. The DESI data, taken alone, was consistent with an equation of state slightly different from -1, with a dark energy density that might have changed over cosmic time. The significance of the deviation from a cosmological constant was around 2 to 3 sigma, not enough to claim a discovery, but enough to attract attention. When the DESI data was combined with other datasets, the significance varied depending on which datasets were included, which was a sign that systematic effects between different observations were contributing to the tension. The community interpreted the result cautiously. It might be a hint of dynamic dark energy, it might be a statistical fluctuation, or an unaccounted systematic. The question is being pursued actively with more data. The story of dark energy's discovery, the two competing teams, the unexpected result, the scramble to verify, has a human texture that is worth exploring more fully, because it is a story about what science actually looks like from the inside, in the moments when it is producing its most important results. Saul Perlmutter began his scientific life not as an astronomer but as a physicist. He grew up in Philadelphia, the son of a chemical engineer and a social worker, and went to Harvard as an undergraduate where he majored in physics. He was drawn to the big questions, the questions about the nature of the universe at its largest scales, and he ended up at Berkeley working in the group of Gerson Goldhaber, an experimental particle physicist who had become interested in using supernovae as cosmological tools. The idea of using Type 1a supernovae as standard candles, as objects with a known intrinsic brightness that could therefore be used to measure distances across the universe, had been around for decades, but the practical challenges were enormous. Type 1a supernovae are rare events in any given galaxy, occurring once every few hundred years or so. You cannot wait for them to happen in a specific galaxy. You have to survey enormous numbers of galaxies simultaneously, watching for the first signs of brightening, and then trigger rapid follow-up observations with large telescopes to catch the supernova at its peak brightness and measure its light curve. In the era before digital sky surveys and automated data pipelines and the internet, this was essentially impossible. By the late 1980s, the technology had advanced enough that it was merely very difficult. Perlmutter built the Supernova Cosmology Project from essentially nothing, developed the survey strategy, the reduction pipeline, the analysis techniques, the network of collaborators with telescope access around the world. He is, by all accounts, an extraordinarily methodical and careful scientist, a person who builds things properly and checks everything twice and does not announce results before he is certain of them. This caution served the project well in its early years, when the technical challenges were enormous and the sample sizes were small. By the mid-1990s, the project had found and measured enough distant supernovae to begin producing cosmological results. The preliminary results, released at various conferences in the mid-1990s, suggested a universe with matter density close to critical, a universe that would expand forever, but only barely, with deceleration slowing it almost to a halt over cosmic time. These preliminary results were widely discussed and moderately believed. And then more data came in, and the preliminary results changed. Brian Schmidt came to the problem from a different direction. He was an American who had done his doctoral work at Harvard under Robert Kirshner, one of the leading observers of supernovae in the world, and who had then moved to the Australian National University in Canberra. Schmidt had grown up in Montana and Alaska, the son of a fisheries biologist, in a family that spent time outdoors and valued independent thinking, and he had a directness and a confidence in his own judgment that sometimes surprised colleagues who expected the reserved formality of academic science. He formed the High Z Supernova Search Team in 1994, drawing together a group of observers from multiple institutions who shared the goal of measuring the deceleration of the universe from supernovae. The team included Rees, then a Harvard graduate student, and several other young astronomers who would go on to distinguished careers. They were the smaller team, with less funding and fewer resources than the Supernova Cosmology Project, and they knew it, and they moved quickly to make up for it. Adam Rees, who did the critical analysis that first revealed the acceleration, is perhaps the most interesting figure in the story from a purely scientific standpoint. He had come to Harvard from MIT, where he had done his undergraduate degree in physics, and he was doing his doctoral dissertation on using Type 1a supernovae as distance indicators, with a specific focus on developing better calibration methods that would reduce the systematic errors in supernova-based distance measurements. His dissertation work produced what is called the multicolor light curve shape method, a technique for correcting Type 1a supernova brightnesses for the intrinsic variation in their luminosities, using the shape of their light curves as a proxy for their peak brightness. Better calibration meant smaller systematic errors. Smaller systematic errors meant the distance measurements were more reliable. More reliable distance measurements meant the cosmological inferences from those distances were more trustworthy. When Rees ran the first analysis of the High Z team's dataset in late 1997, he was using his own calibration method, and he was using it carefully. The result that came out, the universe was accelerating, was so unexpected that his first response was to look for an error in the calibration. Perhaps the distant supernovae were being dimmed by dust in the host galaxies or dust in the intergalactic medium, and that dimming was being misinterpreted as greater distance. Rees checked for dust. The color of the supernova light, which would be reddened by dust, was not consistent with significant dust dimming. The dimming was gray, not reddish, and gray dimming is harder to explain with dust. Perhaps the distant supernovae were intrinsically fainter than nearby supernovae for some physical reason. Perhaps Type 1a supernovae in high redshift galaxies, which tend to be younger and have a different chemical composition, were a different population with different peak luminosities. Rees checked for this using what information he had about the host galaxy environments. He could not find compelling evidence for a luminosity evolution that would account for the anomaly. Perhaps there was a bias in the sample selection. Perhaps the supernovae they had found were somehow a non-representative sample of Type 1a supernovae. He checked the statistics. The selection effects, as best he could determine, did not explain the result. He sent the analysis to Schmidt in November 1997 with a message that was characteristic in its directness. He told Schmidt that the data seemed to require a cosmological constant, and that he had looked for errors and had not found them, and that he thought the result might be real. Schmidt went through the analysis. He reached the same conclusion. He called Kirchner, who had been his dissertation advisor and was now watching his former student navigate one of the most important results in the history of cosmology. Kirchner's response, characteristically, combined scientific rigor with a kind of dark wit. He told Schmidt that the result was either the most important discovery in cosmology in decades or a terrible mistake, and that they had better figure out which. They spent the next several weeks trying to figure out which. The team held teleconferences and email exchanges. This was the late 1990s, before video calls, and the team was spread across multiple continents, working through every systematic effect they could think of. By January 1998, they had not found a systematic error that explained the result away. The result appeared to be real. Schmidt drafted a paper. Rice led the analysis section. They submitted it for publication. At almost exactly the same time, Perlmutter's group had reached the same conclusion. They had a larger data set, they had been working longer, and they had the same result. The universe was accelerating. The two papers appeared essentially simultaneously. Perlmutter's in the Astrophysical Journal, Schmidt and Ries's in the Astronomical Journal. The astronomical community received both papers with a mixture of excitement and skepticism that was entirely appropriate given the magnitude of the claim. Extraordinary results require extraordinary evidence, and the evidence, while good, was not overwhelming. The systematic uncertainties in supernova distance measurements were real and not fully characterized. The samples were not enormous. The result needed to be confirmed. The confirmation came over the following years, from multiple independent directions. Measurements of the CMB by the Boomerang experiment in 1999 and 2000, a balloon-borne telescope that measured the angular size of the acoustic peaks in the microwave background, showed that the universe was spatially flat, with a total energy density equal to the critical density. But measurements of the matter density, from galaxy clustering and from independent arguments, showed that matter accounted for only about 30% of the critical density. Ordinary matter and dark matter together could only make up 30%. For the universe to be flat, for the total energy density to equal the critical density, something else had to make up the remaining 70%. Something with the right properties to produce the flat geometry without the gravitational effects of matter. A cosmological constant, a dark energy, would do exactly this. The CMB measurements and the supernova measurements independently pointed to the same conclusion. The universe was dominated by a dark energy making up roughly 70% of its energy content, with matter, ordinary matter and dark matter together, making up only 30%. Baryon acoustic oscillation measurements, the technique of using the characteristic scale of sound waves in the early universe, imprinted on the distribution of galaxies, as a cosmic ruler, provided yet another independent confirmation. The clustering of galaxies on large scales has a specific preferred scale, corresponding to the distance sound waves traveled in the early universe before recombination. And measuring this scale at different cosmic epochs tells you how the universe has expanded over time. The BAO measurements confirmed the accelerating expansion and pinned down the dark energy density and equation of state in a way that was completely independent of supernovae. By the mid-2000s, the evidence was overwhelming. Dark energy was real. The universe was accelerating. The cosmological constant, or something functionally equivalent to it, was the dominant component of the universe's energy budget. The Nobel Prize in Physics for 2011 was awarded to Perlmutter, Schmidt, and Ries, split between Perlmutter on one side, who led the supernova cosmology project, and Schmidt and Ries on the other, who led the High-Z team. The citation recognized the discovery of the accelerating expansion of the universe through observations of distant supernovae, and it was one of the most clearly motivated Nobel Prizes in recent memory. The Nobel Committee does not often recognize a discovery that was made only 13 years before the prize. It does so when the discovery is important enough that waiting is inappropriate, and the discovery of dark energy was important enough. Rees, who was the first to see the result in his analysis and who was 37 years old when he received the Nobel Prize, described the experience of making the discovery in terms that are worth quoting in spirit, if not exactly. He said that when the result came out of the analysis, his first feeling was not excitement, but dread. The dread of a young scientist who has just produced a result that contradicts everything that was expected, and who knows that if he announces it and it turns out to be wrong, his career will be defined by that mistake. The excitement came later, after the checking and the rechecking and the confirmation, but the first emotion was dread. This is what discovery actually feels like from the inside, in the moment before the excitement arrives. The cold, specific fear of being wrong about something important. The question of what dark energy actually is, not just how it behaves, but what it fundamentally is, what physical substance or phenomenon produces its effects, is the deepest open question in cosmology, and possibly in all of physics. The cosmological constant interpretation says dark energy is the energy of the vacuum, the quantum zero-point energy of all the fields of the Standard Model, somehow reduced by an unknown mechanism to the tiny value we observe. This is the simplest interpretation and the one currently consistent with all data, and it is profoundly unsatisfying because it requires an explanation for the most enormous fine-tuning in the history of physics. The vacuum energy must be cancelled to 1 part in 10 to the 120 by some mechanism we do not understand, leaving a residual that drives the cosmic acceleration. What cancels it? Why does it cancel so thoroughly and yet not completely? Why is the residual the value it is rather than zero or something much larger? These questions have no answer in current physics. The anthropic argument, the argument that the cosmological constant has the value it does because only universes with a cosmological constant small enough to allow structure formation can produce observers to measure it, has been developed most forcefully by Steven Weinberg, who predicted in 1987 before the observational discovery that if the cosmological constant were much larger than a certain upper bound, the universe would have expanded too fast for galaxies to form, and there would be no observers. He predicted that the cosmological constant should be at or below this bound, and the measured value is indeed near but below the bound. Weinberg's argument is often cited as a successful anthropic prediction, though it is contested on the grounds that it requires a multiverse, an ensemble of universes with different cosmological constants to make the anthropic selection work, and the existence of the multiverse is not established by any direct observation. The string theory landscape, the enormous space of possible vacuum states in string theory, each with a different value of the cosmological constant and different physics, provides a potential mechanism for the anthropic selection. If string theory has something like 10 to the 500 different vacuum states, as the landscape suggests, and if inflation samples many of them, then the effective cosmological constant seen by any given observer is the value of the vacuum they inhabit. Most vacua have an enormous cosmological constant inconsistent with structure formation. A tiny fraction have a small cosmological constant consistent with structure formation. We find ourselves in one of the small cosmological constant vacua because we could not exist in any other. The landscape, if it is real, would explain the cosmological constant's tiny value without any fine-tuning. It would be a selection effect, not a physical mechanism. Whether the string landscape is a genuine physical reality or an enormous mathematical structure with no observational consequences is one of the most contested questions in theoretical physics. There is another possibility that is less discussed but more dramatic in its implications. Dark energy might not be constant. It might be changing. A cosmological constant is by definition fixed. It does not evolve, it does not decay, it does not respond to the expansion of the universe. But a dynamic dark energy field, quintessence, or any of its relatives could in principle change over time. It could have been weaker in the past and stronger in the present, or vice versa. It could oscillate. It could in some models eventually reverse sign, turning from repulsive to attractive, changing the fate of the universe from heat death to a big crunch. The recent DESI results, hinting at possible evolution in the dark energy equation of state, are a reminder that this possibility is not ruled out. If dark energy is dynamic, if it is a field with its own physics, Then understanding that physics might eventually explain the cosmological constant problem, the tiny value of the dark energy density might be a consequence of the field being in a specific state with a specific potential energy, a state that could in principle be understood from fundamental physics rather than from anthropic selection. The dynamical dark energy possibility also raises the specter of the Big Rip, the scenario in which dark energy grows stronger over time, eventually overcoming not just gravity at cosmic scales, but gravity at galactic scales, at stellar scales, at planetary scales, at molecular scales, at nuclear scales, tearing apart every structure in the universe. The Big Rip was popularized by Robert Caldwell, who coined the term, and it applies specifically to models in which the equation of state of dark energy is more negative than -1, what Caldwell calls phantom energy. Phantom energy has some deeply strange properties. Its energy density increases as the universe expands, rather than staying constant like a cosmological constant or diluting like matter. As the universe expands and the phantom energy density grows, the expansion accelerates faster and faster, with the scale factor of the universe growing without bound in a finite time. And as the expansion rate grows without limit, it eventually tears apart structures on progressively smaller scales. First, the galaxy clusters are torn apart, their dark matter halos dissolved by the accelerating expansion. Then the individual galaxies are disrupted. Then the solar systems. Then the planets. Then the atoms, the nuclear force which holds atomic nuclei together, is overcome by the accelerating expansion. The electromagnetic force which holds atoms and molecules together is overcome. And finally, at the very end, the fabric of spacetime itself is torn apart. A singularity in finite time, a big rip that ends the universe not in the slow cooling of the heat death, but in a violent, instantaneous dissolution of every structure at every scale simultaneously. The Big Rip is the darkest of the possible futures for the universe with dark energy, and it applies only if the equation of state is more negative than -1. Current measurements are consistent with -1 and do not clearly require phantom energy, but the possibility is not ruled out. And if dark energy is indeed phantom energy, with equation of state slightly below -1, the time to the Big Rip can be estimated, a few tens of billions of years. Not an immediate danger. The Sun has another 5 billion years of main sequence life, but cosmologically close. Close enough that the universe would end before the last red dwarf had burned out, before the degenerate era began, before the black hole era began. The long death described in the previous chapter, the gradual cooling over 10 to the 100th years, would be replaced by an abrupt, violent end in a few tens of billions of years. The heat death would not have time to occur. The second law would not have time to run its full course. Everything would simply be torn apart, all at once, in a final paroxysm of accelerating spacetime that left nothing behind. Most cosmologists do not consider the Big Rip likely given current data. But it is physically possible. It is not ruled out. And the fact that it is not ruled out, that the nature of dark energy is so poorly understood that we cannot exclude the possibility that it will tear every atom in the universe apart in the next few tens of billions of years, is itself a statement about how much we do not know. Let us talk about the people who are right now trying to find out. Because the discovery of dark energy in 1998 was not the end of the story. It was the beginning of a decades-long program to characterize dark energy, to measure its properties with sufficient precision to distinguish between models, to determine whether it is constant or dynamic, to constrain its equation of state to the level where theoretical progress becomes possible. This program is one of the most ambitious in the history of observational astronomy, and it involves some of the largest and most expensive scientific instruments ever built. The Dark Energy Survey, DES, was an imaging survey of the southern sky conducted from the Cerro Tololo Inter-American Observatory in Chile between 2013 and 2019, using a purpose-built camera called the Dark Energy Camera with 570 million pixels covering a field of view several degrees across. DES measured the shapes of hundreds of millions of galaxies, using the subtle distortions produced by gravitational lensing to map the distribution of dark matter and constrain the growth of structure, which depends on dark energy through the competition between dark energy's repulsive effect and gravity's attractive effect. DES also measured thousands of Type 1a supernovae and the angular clustering of galaxies. The results from DES, combined with CMB measurements from Planck, produced constraints on dark energy consistent with a cosmological constant, with systematic uncertainties that were carefully characterized and controlled. The Vera Rubin Observatory, previously known as the Large Synoptic Survey Telescope, or LSST, represents the next major step in photometric surveys. Located on Cerro Pachón in Chile, with a primary mirror 8.4 meters in diameter and a camera with more than 3 billion pixels, the Rubin Observatory will image the entire accessible southern sky every few nights for 10 years, producing a movie of the universe that will detect billions of galaxies, hundreds of thousands of supernovae, and tens of billions of solar system objects. The sheer scale of the dataset, multiple petabytes of data per year, requires automated data pipelines and machine learning algorithms that are themselves research achievements. The dark energy science from Rubin will come primarily from weak gravitational lensing and large-scale structure, and the statistical power of the dataset will allow measurements of dark energy precision that dwarf anything currently available. The Euclid satellite, launched by the European Space Agency in July 2023, is specifically designed to measure dark energy from space, where the absence of atmospheric blurring allows sharper images and more precise shape measurements for weak lensing. Euclid is surveying 15,000 square degrees of extragalactic sky, roughly 1/3 of the entire sky, measuring the shapes of over 1 billion galaxies and the spectroscopic redshifts of tens of millions. The combination of weak lensing and galaxy clustering from Euclid, together with the CMB and other datasets, will produce constraints on the dark energy equation of state at the percent level, enough to distinguish a cosmological constant from many dynamical dark energy models. DEZA, the Dark Energy Spectroscopic Instrument, is a ground-based spectroscopic survey at the Kitt Peak National Observatory in Arizona, using 5,000 robotic fiber positioners to simultaneously measure the spectra of 5,000 objects at a time, obtaining redshifts for tens of millions of galaxies and quasars over 5 years. DA measures baryon acoustic oscillations, the clustering of galaxies on the specific scale of the sound horizon in the early universe, at multiple epochs, tracing the expansion history of the universe with unprecedented precision. It was DAZ's first-year results, released in 2024, that hinted at possible evolution in the dark energy equation of state, though the hint was not definitive. Sol Perlmutter, who shared the Nobel Prize for the original discovery, has continued to work on improving the precision of Type 1a supernova distance measurements. He leads a project called the Nearby Supernova Factory, which uses a dedicated spectrograph to collect detailed spectroscopic data on nearby supernovae, building a reference dataset that can be used to better understand the intrinsic variation in Type 1a supernova luminosities, and to reduce the systematic uncertainties that limit the precision of cosmological measurements. Adam Rees, now at Johns Hopkins University and the Space Telescope Science Institute, has been leading a program called SOAKS, Supernovae, and H0 for the equation of state, using the Hubble Space Telescope to measure the Hubble constant from Cepheid-calibrated Type 1a supernovae with extraordinary precision. It is SOAKS measurements, combined with those of other groups, that have produced the Hubble tension, the discrepancy between the local measurement of the expansion rate and the value inferred from the CMB, which is one of the most significant and unresolved tensions in modern cosmology, and which some physicists believe may require new physics, possibly involving dark energy. The Hubble tension is worth dwelling on, because it connects the dark energy story to a broader crisis in cosmology that is still unfolding. When you measure the current expansion rate of the universe, the Hubble constant, from the CMB, using the standard cosmological model to extrapolate from the early universe to today, you get a value of about 67 kilometers per second per megaparsec. When you measure it locally, using Cepheid variable stars and Type 1a supernovae as a distance ladder, you get a value of about 73 kilometers per second per megaparsec. The discrepancy is about 9%. This may sound small. It is not. The measurement uncertainties on both sides have been reduced to a few percent, and the discrepancy is now more than 5 sigma, the gold standard for a significant result. Multiple groups, using different techniques, have confirmed values on both sides of the tension. It is not a measurement error. Something is different between the early universe and the late universe, and the standard cosmological model cannot explain it. One class of explanations for the Hubble tension involves modifications to dark energy. If dark energy is not a cosmological constant, but a dynamical field that was stronger in the early universe than the standard model predicts, a form of early dark energy, then the sound horizon at recombination would be smaller than the standard model calculates, which would make the CMB peaks appear at different angular scales, and would shift the inferred Hubble constant upward, potentially resolving the tension. Models of early dark energy have been proposed and are being tested against the data. So far, the results are mixed. Early dark energy can alleviate the tension but not eliminate it, and it introduces other tensions with other observables. The Hubble tension remains one of the most important open problems in cosmology, and its resolution, whether it requires new physics or turns out to be an unidentified systematic error, will tell us something fundamental about the universe. Rees has been at the center of the Hubble tension from the beginning, because his team's Cepheid-based measurements are the primary anchor of the local value of the Hubble constant. He takes the tension seriously. He has spent years scrutinizing his own measurements for systematic errors, checking the Cepheid calibrations with multiple independent methods, cross-checking with other distance indicators including the tip of the red giant branch and surface brightness fluctuations. The tension persists. It appears in every independent local measurement he and others have made. He is careful, in the way that careful scientists are careful when they have a result that might be important, to say that the tension might still be a systematic that nobody has identified. But he also says, increasingly, that it might be real physics, that something might be happening in the universe between the early era and the late era that the standard model does not account for, that dark energy might be more complicated than a cosmological constant, that the universe might be telling us something. This is the state of dark energy research in the mid-2020s, a discovery that is firmly established and thoroughly confirmed, a standard model that fits most observations with a cosmological constant, a growing tension between different measurements of the expansion rate that may require new physics, hints from DESI of possible dark energy evolution, and a complete lack of theoretical understanding of what dark energy fundamentally is. The measurements are good and getting better. The theory is inadequate. The gap between what we can measure and what we can explain is as large as it has ever been, and the experiments being built right now, Rubin, Euclid, DESI, Roman, will widen the gap on the measurement side while theorists continue to struggle with the explanation. There is something worth pausing on in this situation because it represents a specific and unusual scientific predicament. Dark energy is not unknown in the way that dark matter is unknown. Dark matter is undetected. We have its gravitational effects but no direct detection, and we are searching for the particle that produces those effects. Dark energy is different. We have characterized its properties, its energy density, its equation of state, its spatial distribution, with considerable precision. We know what it is doing to the universe. We do not know what it is. The distinction is important. Dark energy is not a gap in our observations. It is a gap in our theory. We can measure it, but we cannot explain it. The data is there. The physics to interpret the data is missing. This is, in some ways, a more uncomfortable scientific situation than having missing data. Missing data can be addressed by building better instruments, conducting more observations, increasing the statistical sample. Missing theory is harder. It requires a conceptual breakthrough, a new idea, a new framework, a new way of thinking about the vacuum and its energy that resolves the cosmological constant problem and explains why the vacuum energy has the value it does. Such breakthroughs cannot be scheduled. They do not arrive because a funding agency has allocated resources for them. They arrive when someone has the right idea, and the right ideas come unpredictably from directions that are not obvious in advance, from people who are often not the most senior or most credentialed in their field. The history of physics is full of examples. And the history of dark energy, discovered by a graduate student running an analysis at Harvard, confirmed by two competing teams that spent years assuming their own data was wrong, is a reminder that the right answer often comes from an unexpected direction. The universe is accelerating. It has been accelerating for about 5 billion years, roughly since the sun formed, roughly since the solar system came into being, roughly since the conditions for life on Earth were being established. Before that, the universe was decelerating, matter dominated, and gravity was winning. The transition from deceleration to acceleration occurred when the energy density of dark energy became comparable to the energy density of matter. Before that transition, the universe expanded more slowly and gravity assembled structure, galaxies, clusters, filaments of the cosmic web, from the small density fluctuations imprinted by inflation. After the transition, the expansion rate increased, the growth of structure was suppressed, and the universe entered the dark energy-dominated era in which we now live. This timing, the fact that we live in the era when dark energy has just recently become dominant, is itself suspicious, and it connects to what cosmologists call the coincidence problem. The energy density of matter decreases as the universe expands, As the universe gets bigger, the same amount of matter occupies a larger volume, and the energy density falls. The energy density of a cosmological constant does not change as the universe expands. It is a property of the vacuum, and every cubic centimeter of vacuum has the same energy density regardless of how big the universe is. So the ratio of dark energy density to matter density increases over time. In the past, matter dominated and dark energy was negligible. In the future, dark energy will dominate overwhelmingly and matter will be negligible. Right now, they are comparable, within a factor of 3. The fact that we live at the precise cosmic epoch when the dark energy density and matter density are within a factor of 3 of each other, out of the entire history of the universe during which they could have differed by many orders of magnitude, seems like an extraordinary coincidence. Either we are profoundly lucky, which is hard to accept, or there is some mechanism that makes the dark energy density track the matter density in some way, keeping them comparable, a possibility called dynamical dark energy tracking solutions. Or the coincidence is a selection effect that observers can only exist in the era when the universe has cooled enough and formed enough structure, which happens to be the era when dark energy and matter densities are comparable. The coincidence problem has not been resolved. Like the cosmological constant problem, it sits in the foundation of dark energy physics as an uncomfortable reminder that we do not understand what we are seeing. We have measured the dark energy density. We know its value. We do not know why it is that value. We do not know why it is comparable to the matter density at this time. We do not know what happens to it in the far future, whether it remains constant and drives the universe toward heat death, or grows larger and drives a big rip, or eventually decays and allows the expansion to decelerate again. We do not know what dark energy is. We know what it does. And what it does is extraordinary. It is accelerating the universe. It has been doing so for 5 billion years. It will continue to do so, unless its properties change in ways we cannot predict. For all the cosmic future, increasingly dominating the dynamics of space-time, pushing galaxy clusters apart until they are beyond each other's horizons, isolating our local group from the rest of the observable universe on timescales of a few 100 billion years, ensuring that any civilization that survives to the deep future will live in a universe that appears to contain only a single island of galaxies surrounded by empty space, with no evidence that the rest of the universe, the 2 trillion galaxies visible today, ever existed. This is already happening. Galaxies beyond a certain distance, those whose recession velocity exceeds the speed of light due to the expansion of space, are already beyond our cosmological horizon. Their light will never reach us. They have already, from our perspective, effectively ceased to exist in any observable sense. And the cosmological constant, if it persists, will cause more and more galaxies to cross this horizon as time goes on, disappearing from the observable universe one by one, swept beyond our reach by the acceleration. The universe visible to us is shrinking, even as the universe as a whole is expanding. We are losing access to the cosmos faster than we are gaining it. The 2 men who led the teams that discovered this, Perlmutter and Schmidt, shared a Nobel Prize stage in Stockholm in December 2011, alongside Rees, who received his half of the prize. The speeches that night were characteristic of each person. Perlmutter spoke about the scientific process, about the importance of being willing to be wrong and correcting yourself when the data demanded it, about the extraordinary privilege of being part of a discovery that changed the way humanity understood the universe. Schmidt spoke with his characteristic directness about the fear he had felt when the result first came in, the specific, concrete fear of a working scientist who has a result he cannot explain and cannot make go away, and who knows that announcing it will make him a target for every critic who has ever wanted to catch someone making a claim they cannot support. Rees spoke about the graduate student experience, about what it is like to be 27 years old and running an analysis and seeing something come out of it that does not make sense, and having no senior person in the room to tell you whether you have made a discovery or a mistake. All 3 of them, in their different ways, said that the discovery was not what any of them had expected to find. They had set out to measure the deceleration of the universe. They had found the acceleration. They had checked their work. They had published. The universe had turned out to be doing something nobody had predicted and nobody had expected, and the task now, the task that continues today, in the great surveys and the refined analyses and the ongoing theoretical effort, is to find out why. We do not know yet. The universe is 68% dark energy, and we do not know what it is. The vacuum of space is filled with something that is accelerating the expansion of the cosmos, and our best current theory gives a prediction for its magnitude that is off by 120 orders of magnitude, and we do not know why. The most abundant component of the universe is the most mysterious, the force that will determine the ultimate fate of everything, whether the universe dies in heat death or in a big rip, or in something we have not yet imagined, is the force we understand least. Albert Einstein added a term to his equations in 1917 to make the universe static. He removed it when Hubble showed the universe was expanding. He called it his greatest mistake. The universe has turned out to contain exactly that term, in the exact mathematical form Einstein used, driving not a static universe but an accelerating one. The greatest mistake of the greatest physicist of the 20th century turns out to have been no mistake at all, just a term added for the wrong reason, which turned out to be present in reality for reasons we still do not understand. The universe is strange in ways Einstein could not have anticipated, in ways that nobody anticipated, in ways that two teams of astronomers in the late 1990s spent years assuming were errors before accepting that they were reality. It is accelerating, something is pushing it, we don't know what. And finding out, understanding the nature of dark energy, solving the cosmological constant problem, explaining the coincidence problem, mapping the equation of state to sufficient precision to distinguish between models, is one of the most important and most difficult scientific tasks of the coming century. Two teams of astronomers, working in competition and in ignorance of each other's results, each convinced their own data was wrong, found the answer to a question they were not asking. They went looking for the deceleration of the universe. They found the thing that will determine the universe's fate. They found it by measuring the brightness of exploding stars in distant galaxies, a technique that their predecessors would have found almost incomprehensibly sophisticated, using telescopes that were the most powerful of their time, in an era when the technology had just barely reached the threshold of making the measurement possible. The universe waited 13.8 billion years to be measured. It was patient, and when it was measured, it revealed something nobody expected, something that required a complete rethinking of the energy budget of the cosmos, something that pointed to an unknown substance making up 2/3 of everything that exists, something that carries within it the answer to the ultimate question of what happens in the end. We are working on the answer. The instruments are running, the data is coming in, and the universe, dark and expanding and accelerating, is not telling us yet.